So thank you very much, Dr. Szymczak, for this excellent speech. Now I think that we know everyone about the life of the Dalibor Dobrovolsky. So everyone has a feeling that the place to locate the plaque of the milestone in Szczecin, this is a proper place because the memory of Dalibor Dobrovolsky will live here forever. We know from the speech that Dalibor Dobrovolsky, it was an inventor of the AC machines, but of course, since that time, the development of this machine is coming, and of course, in the case of the more compact machines, more efficient machines, the development is still active today. So therefore, it's my pleasure to move to the second speech, which is related exactly to this topic, entitled Performance Evaluation of the Three-Phase Induction Machine between 1945 and 2020. And the speaker is Professor Aníbal de Almeida. So, dear professor, please, do you prefer to have a speech from that place? Okay, please, floor is yours.
Hello, hello. Good morning. I want to congratulate the organizers, IEEE, who is represented in this meeting at the highest level through President Kathleen. I want to also congratulate the Polish Association of Engineers and also the Szczecin University of Technology for having the idea of honoring one of the founding fathers of electrical engineering. And in my overview, I will try to locate the importance, why this invention was a breakthrough, and what's in the pipeline in terms of evolution. Technology is always, Michael, yeah, sure. So, never ceases to exist. There was a very important change in the world economy with the Industrial Revolution, which was initiated by using water power, namely textile companies. But when you are using energy from nature, you run into a problem. Sometimes there is no water. So fortunately, around the same time in England, it was developed a steam engine. So with steam, if you have enough coal or wood, the weather is not a problem. So basically, you change from the first factories based on water power to drive power based on steam power. Even so, there is a common link between the two technologies. Namely, you have a prime mover and you had to distribute mechanical power inside the plant. You had shafts, belts, a mess in terms of operation. Fortunately, by the mid-19th century, electric motors were developed. I would say that the key step in terms of industrial motors was developed by Siemens. Siemens was able to develop fairly robust, I say fairly because fairly robust DC motor, which started to be used in large scale after the mid-50s. And this graph, you see the water power dropping from the mid-70s, dropping steadily, whereas steam power was growing very fast. But then, as the 19th century came to a close, there was a very fast change to electrification. It's really, if you think about it, in a space of a few years, you change from steam to electric motors in industry. And when we situate how this evolution happened, So we started basically the most important driver in the Industrial Revolution was the steam engine. And then we moved to the second Industrial Revolution, which was based on electrification. And one of the key machines for electrification is electric motors. So it started, and electric motors have been evolving with different technologies, different capabilities. Then, very importantly, around 1970, we had the invention of microcomputer. Intel invented the microcomputer, and the use of intelligence, of electronic intelligence, made sophisticated automation possible. And by the way, it also improved a lot how motors can be used. So there is a synergy between motors and electronics, as I will say later. And more recently, we are running into Internet of Things. That's also very important for motors. And more, the use of cognitive systems and artificial intelligence. So I would say that we have been going through a change that is accelerating, by the way. Our hero, our superhero, which we are honoring today, was really an outstanding character. He was able to see very far in the future. There was not yet three-phase system, but he imagined that if he had a three-phase supply, he could produce a rotating field and a very robust motor. So this is what makes a genius, to be able to see things that are not yet there. So basically, the evolution for the squirrel cage induction motor is a very, very significant change in terms of capabilities compared with existing technologies. The induction motor compared with the previous motors, like DC motors, is much better in all respects. It has a higher power-to-weight ratio, is much more reliable, much longer lifetime, more efficiency. It can be scaled. You can make very tiny motors. You can make multi-megawatt motors. So it's really absolutely amazing. And another capability that the induction motor also has, compared to other competing technologies, is its capability for direct online starting. Some sophisticated motor technologies are very good, but they need electronic controls. With induction motor, you can basically start a motor directly from the network, which is very convenient. So, as it was already said by Professor Piotr Szymczak, Dobrowski introduced in the market through AEG the first squirrel cage induction motor in 1891. And since then, a lot of evolutions have been implemented. The first induction motor was massive, 4.4 kilowatt motor, weighed more than 300 kilos, which is extremely heavy. So as you can see in this graph, there was a trend, a very significant trend to make lighter motors. Of course, the motor is lighter, uses less metal, it's cheaper. It's also important that the motor is not expensive. And you will notice at the end that the trend to decrease the weight reversed. I will explain later why. It's sort of paradox. The weight keeps dropping very fast and suddenly starts increasing again. So in terms of why this happened, several important improvements were carried out. First of all motors need support for the shaft. And the introduction of ball bearings produce a much more compact and much more reliable type of support to the shaft. Then other major improvements had to do with the insulation. Insulation was thick and didn't last long, so an evolution in insulation was also very important. Magnetic. In a motor, you need the coils, which are run with current to produce a magnetic field, and you need a magnetic circuit to channel the magnetic flux. So there were also very important changes that I will show in more detail on how these improvements have been carried out. So basically, all the motors suffered a very strong evolution in terms of the materials and the construction and design of the motor itself. This shows several cutaway views of insulation, starting with cotton, then with silk, then a mixed silk with varnish, and finally varnish. So varnish is much better because it withstands higher temperature, so it's going to last much longer, and also because varnish is a good conductor of heat. And when you have a coil in which you have air voids, the transmission of heat is not so efficient. So it's very important, makes the winding more compact, and the transmission of the heat also improves. And this is an overview on how motors evolved over the past 1 century, starting with open frame motors, large open frame for the same size, for the same power. All these motors are 11 kilowatt. So there was a drastic reduction in size and weight. And if you notice, the motors, the ones on the left are NEMA, that's North America market. The ones on the right are Europe, IC. An important evolution that you may see is initially you start with open frame motors, and later you go to enclosed motors. Why? If you are able to decrease the losses, you are and avoid the entry of foreign materials into the motor, that's the way to do. So you close the motors after there is a significant reduction in the losses. You have a fan that is coupled to the shaft. You will see that the more recent motors are, the back part of the motor is a bit longer to accommodate the fan. So today, the vast majority of motors is totally enclosed fan motors. By the way, I didn't refer, induction motor is more than 100 years old, right? To be more precise, it will be something 130, more than 130 years old. But if you go to industry today, more than 90% of the motors are still three-phase squirrel induction motors. This shows how the technology, after suffering some improvements, is still is the workhorse of industry. So regarding one of the key issues, when you have a motor, you have current in the windings, and when you have current going through the windings, you have losses, and you have a challenge on how these losses can be removed. And the new insulation, varnish insulation, was a key step because it improves the release of the heat from the grooves to the laminations, and then you notice that on the outside, on the case of the motor, you'll see the fins. The fins on the out case of the motor are to increase the external surface in order to improve the heat transfer. This is an evolution on a 3-point kilowatt motor from Hitachi, showing the different evolutions on the insulation, on the bearings, on changing the squirrel cage from copper to aluminum, and then on the case from going to cast iron to steel or even to aluminum. Closer. Thank you. Is it okay now? Thank you. So during these 90 years, the weight of the same motor dropped by a factor of 18 times lighter. When it comes to magnetic materials, there is also a very strong improvement in several ways. The magnetic material, was made with higher permeability, with higher resistivity by adding silicon to the iron, and also very important by thinner laminations. Nowadays, the laminations which are used have about 0.3 of a millimeter. But for transformers, an American company called Allied Metal, some 2 decades ago, developed a material called amorphous metal. And these plates are only 25 microns thick. So there are some companies experimenting with new motors that use this amorphous metal. And basically, you slash the magnetic losses by 80%. You may see this happening coming into the market. So still a new improvement for motors, which might be possible in the near future. You see here the evolution of motor efficiency for different power ranges during the last 80 or 90 years. So you see something strange in the middle, that the curves, I don't have enough power here to project, but there are 2 lines that somehow are not improving much, and these lines refer to periods during the 60s and the 70s. During the 60s and the 70s until the first oil crisis, electricity was very inexpensive, so manufacturers start making motors as cheap as possible by reducing the amount of copper and the amount of steel, and this you had very inexpensive motors, but not a good choice because they use more electricity. So on a life cycle cost basis, it was not a wise decision to choose this type of technology. And this again shows how 3 manufacturers, their motors improved through the years. You see the period of stagnation again, 60s, 70s, but there is a common situation. After the 90s, all improved very fast. Why is this? This because of incentive programs started in North America and also minimum efficiency standards. This was a stimulus for the motor manufacturers to develop introduce into the market high efficiency motors. So the same story, this type of stagnation in the 70s and then followed by an increase. When we look at the induction motor is quite good in terms of efficiency. You see, we are speaking motors that, depending on the power, have a full load efficiency, say between 80 and 95%, but still they have losses. So how can you cope with this? The highest losses, the largest, are the stator losses, the windings. And what can you do here? You can improve winding techniques. You can reduce the coil heads. You can use concentrated windings. So manufacturers are designing in this perspective. Rotor losses. This is the principle of induction motor by using squirrel cage. By using squirrel cage with larger cross section, you are able to decrease the rotor losses. If I would point a less good aspect of induction motors, I would point that the rotor in induction motor is always late. He's always trying to get the rotating field. He moves after the rotating field, but never is able to catch it. And there is a penalty, and the penalty are the rotor losses. If you are able to develop a technology that the rotor accelerates and catches the synchronous rotating field, no more rotor losses. You slash, rotor losses are magnetic and electric. You cut them to zero. If the slip is zero, you still have the mechanical losses, but that would be a tremendous improvement. And some manufacturers are working on this, on a kind of hybrid design in which the motor starts by induction and then runs at synchronous speed. Straight losses can be reduced to better design to minimize leakage. Core losses, better magnetic materials. It's happening progressively, particularly if we go into amorphous. Don't think it's something that cannot be done. In Japan, 50% of distribution transformers already use amorphous metal. Because in a transformer, it's connected 24 hours per day, and most of the losses in a transformer are distribution transformer are iron losses. So when they move to amorphous, it's really very important. So in this graph, there is an overview of the areas in which induction motors have evolved a lot during the last 100 years. And all basically go into the same direction. Make the motor more efficient and more reliable. And the two things go together. Why? Because what can go wrong in an induction motor? Basically, mostly the windings and the bearings. After the introducing the new class of varnish that can operate continuously at 100 degrees C, these windings last extremely long periods. Bearings, you have mechanical wear, but the mechanical wear in the bearing is a function of the bearing temperature. So if the motor is running cooler, the lifetime of the bearing will also be longer. So there is a positive coupling between efficiency, reliability, and maintenance. So I think induction motor was a great invention, is getting even better with this type of progressive improvements. This is an interesting figure. When there was the introduction of energy-efficient motors in the 90s, you see two motors sharing the same case. One is a standard motor. From the outside, they look the same. But if you cut the case, what you see is the efficient motor, basically, inside has more iron and more copper. Very easy to understand. Basically, for the electric losses depend on the resistance of the windings. So if you put more copper, you decrease the copper losses. With magnetic steel, the same story, because the magnetic losses are proportional to the square of the flux density. So if you use more magnetic steel, you are decreasing the density. So if you want to explain to a person who is not an engineer what's the difference between the two motors, the more efficient motor has more copper and more steel. To say in very, very simple words. So is it still possible to improve the induction motor? Yes, it is. So we already spoke about new magnetic materials. The use of hybrid rotors to make the motor synchronous. And there are some people, particularly I know a company who is working on axial flux motors. Axial flux motors are more compact and allow the use of concentrated windings. So I'm not aware of an induction motor of axial flux on the market, but there are axial flux motors. If you go to modern elevators use axial flux motors, but it's not induction motors, they're permanent magnet motors. So the field is still evolving. And in terms of efficiency, before the year 2000, when you buy a motor in Europe and you look at the nameplate, you had power factor, you have current, you have voltage, but no efficiency. A shame. You buy something that uses a lot of electricity and the efficiency is not written on a nameplate, not anymore. Now, IC is determined as created, like hotels have classes, 1-star, 5-star hotels, motors also have stars. So now you have the classes which are defined by, on a world basis, by IEC. IEC is adopted everywhere, China, USA. So these classes, and as we see here, there has been a trend moving up the scale on these efficiency values. And in terms of engineering, there are many research groups around the world trying to improve the performance of the motor in the lines which I mentioned to you. And in the market right now, you have induction motors going from I1 to I4. Why not I5? Because the amount of active materials would make the motor too heavy. So to go to I5, there are some technologies, namely permanent magnet synchronous motors or synchronous reluctance motors, which can achieve I5 performance with a smaller amount of active materials. Why is it so important to keep moving the efficiency? Because motors in total use more than half of total electricity used in the world is used by motors, not just in industry. When you go to buildings, now not just elevators, heating and cooling are being done more and more with heat pumps. So there is an ongoing electrification of buildings. And the importance of motors, which is already more than half, it's become even more important. So in terms of policy towards sustainability, it makes a lot of sense. Minimum efficiency standards around the world. North America was the pioneer, 1997. DOE published the first energy efficiency standards, and then it has been a virtuous circle. Other countries are moving, so it's a success story because it's a win-win situation for everybody. People save money in their companies by using more efficient motors, and because we use less energy, there is less pollution. So this is really moving. So right now, the majority of the large countries in the world has super premium motors. In Europe, we call I3. But you see the dark blue area is I4 motors. I did a study for the European Commission on the definition of this new standard, which is cost effective. So since July 2023, in Europe, it is compulsory to use I4 motors from 75 to 200 kilowatts, and the standard is going to be extended because the manufacturer said, well, if we have to make I4 motors for smaller motors, we have time to adapt. But the idea is that very soon in Europe, I4 will be compulsory. DOE is also projecting to do the same by 2027. So this is quite a successful story, the motor market transformation which has occurred around the world. The International Energy Agency, in the net zero roadmap to 2050, states that by 2035, all motors sold must be i5. So because of their importance, it's really very important that we look. So finally, in the beginning, when I spoke about evolution of industrial revolutions, I mentioned that we are witnessing introduction of technologies which are synergistic, namely electronics. An induction motor, if you connect it to the grid, basically operates at almost constant speed. But if you connect it to electronics, you can change speed and can change torque. You can optimize. You can do energy recovery, like in an elevator. When you go up, you go down, you can recover the energy. So this is very important to consider. It's like an orchestra. The motor is like the heart of the system, but all the rest is also very important and has also a lot of influence. This is an example of pumping system in which you may save 5 or 6% with the motor by putting an efficient induction motor. But if you optimize the whole system, the pump, variable speed drive, you save maybe 50, 60%. So digitization, also very powerful. New technologies related to cognitive system and artificial intelligence. So I would say that motors will keep being more and more important, and I think the future is bright, and we have to thank to people like Michael Dobrowski for his outstanding invention. Thank you for your attention.